Let's look at how we graph y equals mx plus b. We need to remember that m is the slope, and it's made up of the rise over the run, and b is the y-intercept, or the location where the line will cross the dependent axis. To graph any line, we need to be able to identify its y-intercept and its rise and run. For the line y equals 3 over 2x minus 4, the y-intercept is negative 4, the rise is 3, and the run is 2. We will begin by plotting the y-intercept. We start counting from the origin and count down 4 spaces because the y-intercept is negative 4. We put a point at this location. From there, we will count up 3 since the rise is positive 3, and right 2 because the run is positive 2. We will plot a point at this new location. From here, we will repeat the rise and the run count and plot points as many times as we can before we run out of room on the graph. We will draw a line through all of our points and put arrows at both ends of it. Finally, we will label our line with its equation. So that's how you graph a line in the form y equals mx plus b. This collection of y equals mx plus b equations illustrates the unique situations that you might come across when you're asked to graph a line in the form y equals mx plus b. You can pause the video now and try them on your own, or you can continue to watch the video and graph them along with me. Remember that to graph a line in the form y equals mx plus b, we need to identify the y-intercept and the rise and the run. The m value in this equation is just a 4. We have a rise that is apparent to us, but not a run. We know, though, that a whole number can be written over 1, so this will be our run. We will plot the y-intercept of 1, and then count 4 up for our rise, and then 1 to the right for our run. We will plot a point here, and then continue this rise-run pattern until we run out of grid space. We will draw a line through our points, add arrows to both ends, and we will end by labeling the line with its equation. This equation does not provide us with a b value. We know from our work with partial and direct variations that this means we must be dealing with a direct variation. In Unit 5, this would tell us that the line starts at 0. In Unit 6, we know that our line will pass through the origin. So we will begin by plotting our y-intercept at 0, and from there we will count down 2 to reflect a rise of negative 2, and over right for a run of positive 3. We will plot a point here, and then we will repeat this rise-run count as many times as we can. We'll connect the points, draw arrows, and label our line. When we find an equation in the form x equals, we know that we're dealing with a vertical line. This is one of our special case lines. The negative 4 tells us where the vertical line will cross the x-axis. So we'll plot a point at negative 4 and we'll draw a vertical line through it. When no coefficient is out front of a variable, we know it must be a 1. For our m value in this case, we can add a run of 1 as well. This means that both our rise and our run are 1. So we will start at the y-intercept of positive 4, and then we will plot up for a rise of 1 and over to the right for a run of 1. We will repeat this rise-run count until we run out of grid space, and then we will draw and label our line through the points. This is an unusual way for a y equals mx plus b to be presented. It is not often that we see a negative rise and a negative run. Let's explore why. We can plot the y-intercept of negative 2. From there, we will count a rise down for negative 2, and then a run left for negative 3, and we will plot a point at this location. Note that it's unusual to have to plot a negative run to the left. In all of our other examples, and in most cases, we plot our run to the right because we typically have positive runs. For this situation, we will continue to plot down 2 and left 3 until we run out of space on our grid, and then we can draw and label our line through the points. If we look at our completed graph, we can see why this is an unusual situation. Our graph now reflects a positive correlation. This is because when a negative is divided by a negative, as the rise and the run would be divided, we'd get a positive. Instead of plotting this line as it was given to us, we would likely fix the signs before graphing. We can verify that this would work by plotting the y-intercept of negative 2 and then counting up 2 and over to the right 3 repeatedly. This would provide us with the same line that we originally drew and confirm for us that a negative divided by a negative is in fact a positive. When a negative is out front of our m value and not assigned to either the rise or the run, we will move it to the top so that we can make the rise be negative. It is easier for us to visualize and plot a negative rise as falling down. By keeping our run positive, we will know that we will always count right for the run and avoid being confused as to whether we need to go left or right when we are using our slopes to plot our points. We will begin by plotting our y-intercept at +6 and then go down 1 and right 2 repeatedly to plot our other points. To finish, we will connect our points and label our line. If we plot two y=mx+b's on the same grid, we can find their point of intersection. It is helpful to do this using a different color for each line. We will use our regular process for graphing the lines. We start with the y-intercept of the first line and then count the rise and the run repeatedly as many times as our grid allows. We'll do the same for our second line in another color. We can see the point where the two lines meet and label it with its coordinate. In grade 10, you will learn how to find the point of intersection with algebra, but for now, we are happy to find it on a graph. Don't forget to watch out for special case lines. If you find a line in the form x equals a number, you'll know it's a vertical line with an x-intercept of that number. Similarly, if it's in the form y equals a number, you're going to know it's a horizontal line through that number. In this case, our first line is horizontal and has a y-intercept of 5. We can plot it easily as long as we recognize that it is a special line. Our second line will begin at the y-intercept of -2. Our rise will be 3 up and our run will be 1 right. Once again, we will continue plotting the rise and the run repeatedly until we run out of grid space. We can identify the point of intersection and label it with its coordinates. If you've watched to the end of this video, you've seen a variety of y=mx+b and special case lines being graphed. It's time to practice some on your own. This is an important skill to develop, and you will use it frequently both in the rest of this unit and in all levels of math moving forward. Good luck with your practice. Don't forget to come back to reference the examples in this video if you need some help.